Assalamu alaikum. This is lecture number 8, Physics 281. In this lecture, I will continue discussing the coupled oscillations of a loaded string. In the previous lecture, we reached this equation that gives the amplitude of the earth particle. This is its thing, and the displacement, the adjacent the displacement between two adjacent masses is equal to A. In this picture, this is the displacement of the earth particle relative to the equilibrium position, and this is the displacement of the r plus 1 particle, and this is the displacement of r minus 1 particle. Now if we rearrange this equation, we get this expression. If you look at this expression, the right hand side is independent of the index r. Now simplifying the right hand side and define omega 0 square as t over ma, we get this expression. For a particular omega, say omega sub j, the right hand side, as I said, is independent of the index r. Now let's assume that the amplitude of the earth mass is given by a sub r equals some constant c times sine r theta. Now to satisfy the boundary conditions, let's insert e sub r in this equation and then simplify the sine function. We get this. We finally find that this ratio is given by 2 cosine theta. Now solve for omega square. We get this expression, omega square equal to omega 0 square 1 minus cosine theta. I'll call this as equation number 1. Now for the boundary conditions, at r equals 0, a0 is 0, c sine 0 is 0. At n plus 1, and plus 1 is the right end of the string, so the sine of n plus 1 theta is 0. It means that the argument of the sine function must be integer j, say, times pi. J is equal 1, 2, 3, etc. Therefore theta sub j, I give an index j for theta now, is equal j pi over n plus 1. Now insert this theta in a sub r. We get a sub r equals c sine r pi sub j over n plus 1. I call this equation number 2. This is the amplitude of the earth particle. Now we have omega square is given by this expression, and minus cosine theta is sine square theta over 2 times 2, so we get 4 here. Now solve for omega sub j. This is the modes number j, which is equal to omega 0 sine pi sub j over 2 into n plus 1. N is the number of particles. Now for the displacement y, we have a sub r cosine omega t. That's the solution of the equation. So y sub rj, r is the index for the earth particle, and j is the mode index, which is equal a r sub j times cosine omega j. Substitute for a sub rj. We get this expression. That's why r sub j is equal a function of t c sub j sine r by j over n plus 1 times cosine omega j. This is the displacement of the earth particle at mode j. This thing is the amplitude. Now if we plot pi times j over 2 n plus 1 versus omega g, we get the sine curve like this. The maximum is at occurs at pi over 2, 3 pi over 2, and it's equal to omega 0. This is the maximum frequency, which we call it cutoff frequency. Now let's look at various normal modes. That's we have to vary j. We have y sub rj is given by this expression, and omega sub j is given by this expression. Now for one mode j equal 1, we have omega 1. Substitute here, omega 1 is 2 omega 0 sine pi over 2, which is 1, which is 2 omega 0. The problem we solved in the previous lecture. Now let's take n to be 5 particles. That the string consists of 5 particles. In this case, a sub r1 is c1 sine r, which is 5 pi over n. R is the number of particles over n, which is 5 plus 1, which is 6. The first index refers to the particle number. The first index refers to the mode number. So we have for A11, particle number 1 at mode 1 is given by this, which is C1 sine pi over 6, which is equal half C1. A2 for particle number 2, this is particle number 1. This thing is in this plot. This is T versus the amplitude, vertical amplitude. For the second particle, A21 is sine r is 2 pi over 6, which is square root 3 over c. This thing is the square root 3 over 2. A31, particle number 3, which is c1 sine pi over 2, which gives you c1. This is c1, the maximum. And A41 is given by this. Similarly for A51, A610 is the right end, which is 0, and A01, which is the left end, which is 0. This is the boundary condition. The ends are fixed, doesn't move. Now this is the shape or how A varies with T at mode number 1, omega 1. Now for j equal to the second mode, similarly we have to put r equal to, we get 2 pi over 6. For A12 we get this. For A2 we get this. For a particle 3 at mode 2 we get 0. For 1 and so on. This is 5, 2, and the ends are at 0 because they are fixed. So we get this sort of thing. This is the displacement of particle 1, particle 2, particle 3, 4, 5. It looks like a sine wave. Now to see how difficult to solve the determinant, we already derived this equation of motion. Now simplifying to get y double prime r plus 2 omega 0 square y r minus omega 0 y r plus 1 plus y r minus 1 equals 0. Let's take one particle, that's r equal 1. We get this equation. We already did this problem. Also for n equal 2, we already did this problem in the previous lecture. We get two equations. We know that y sub r is a sub r e to I omega t. For n, now for n masses, we get n equations of this form. You have to put 1, 2, a0 is 0 because the left end is fixed, up to a sub n plus 1. A sub n plus 1 is 0 because the right end is fixed. Now put these equations in a matrix form. This is the vector a1, a2, which represent up to an, which represent the vertical displacement, and this is the coefficients. Now this determinant is very hard to solve. Now let's move to derive the wave equation. We have this expression before. I will let a equal delta x, then the right hand side become t over m delta x of y at x sub r plus delta x minus 2 y at xr minus y at xr minus delta x. Now if we let the mass goes to rho is the linear density, kilogram per meter, times delta x, then the right hand side becomes t over rho 1 over delta x square y of at x sub r plus delta x minus 2y at x r minus y at x r minus delta x. Now if delta x, take the limit delta x approaches 0, we get t over rho times this expression. This expression represents the second derivative of y with respect to x. That's d2y by dx square. Now this thing is equal to the left hand side, which is d2y by dt square. Therefore we get d2y by dt square equal t over rho d2y by dx square. Now if we look at this constant and make a dimensional analysis, it's a square of a velocity. It's meter square per second square. It represents the speed of the wave. Now this is the final expression for the wave equation. Thank you.